Hi everyone. I did my final project on NoProp, which is an algorithm called no propagation. With the title of "Does model training without full back propagation improve catastrophic forgetting?" For this semester's deep learning course. So to intro that, as we all know, gradient descent via back propagation can be computationally and temporally expensive. It's also the kind of cornerstone of deep learning, modern deep learning. We need it to get the weights right in our network. NoProp is an algorithm that offers a solution to that kind of trade-off that I was just talking about via an application of diffusion models. That is to say, you train noise classification labels on input data, the images, in localized discrete blocks, and only back propagate on those blocks. So, as you can see in this architecture here, what that ends up looking like in practice is you have your original labels, Z0, and then these discretized blocks from then on out, Z1, ZT minus 1, ZT, T, independent blocks that end up getting trained and back propagated on. So among the kind of compute reasons that I was just talking about, storage reasons of when you're training extremely large neural networks of billions of parameters, it tends to be very obviously computationally expensive, and this NoProp algorithm can, in some cases, nearly half that computational cost. Another reason that motivated the researchers that came up with this paper earlier this year was that this application of diffusion models in these sort of localized blocks, there's more biological plausibility to the algorithm than in full back propagation. Insofar as when you or your brain learns something and it's making these connections within it, they're happening locally, right? Like they can move out from a localized area. They have some radius, if you will, but they all start kind of locally, which is effectively this idea of these noise labels and back propagating on these localized discrete blocks, vice the whole network, which I don't necessarily think biological plausibility is the end all be all, and whether a neural net architecture or algorithm is good, but it's certainly something interesting to think about, and I think consider in each of these designs. So, to go a little bit more in depth on what I was talking about before, you can see here, this is our noise schedule for those discretized blocks. We ended up using a logarithmic one, the original paper, and their official kind of Python implementation of it chose a linear one, but we got pretty abysmal results with that. So this essentially gives you those discretized, like how noisy are the labels going to become on your data. Here, these X's are your input image datas, which get ran through a convolutional neural network here. And so then what ends up happening is you combine the noise labels, this image, the feature that's going to run through the CNN, combine those, and then run that input through this multi-layer perceptron network. There are 10 discrete versions of that in each of these parts. And then at the end, once you run through all these MLPs, you get your predicted value. So to make that a little bit more clear, hopefully, this is from their paper's implementation, which I thought did a really good job at explaining it in a pretty simple way. A run through of the algorithm. So to simulate one epoch of training, batch size 3, say there's 3 classes: cat, dog, bird, and we were using MNIST, so it would have been 0, 1, 2 or something. The diffusion steps in this case was 2. We used 10 in ours. But what that ends up looking like, so you batch your data. You have 3 images. You assign them the labels. You one-hot encode them, which we've all done that, right? So you end up getting this tensor that's one-hot encoded: cat, dog, bird. Then next, that's when you perform your forward diffusion, your forward kind of pass. So you have that noise schedule that I was showing you before, this alpha. So you get this, in their case it goes 1, 0.6, 0.3, which then you take those clean labels. The first one, Z0, is just equal to those clean labels. And then T1, you have a slightly noised version of all these labels, and then T2, you have a more noised version of these labels. But you can tell if you were to take like the argmax of each of these, you're going to end up getting the correct index. Definitely here, and even here you would get the correct index. You'd have to apply even more noise to not be able to do it with just a straight argmax. So then from there, you take those image features like you were talking about, and then you take the noise labels, and then throw it into the multi-layer percept time network, which spits out a prediction, this sort of U hat in this case. And then from the prediction, which again is approaching the actual value that you're going for, is what you hope. You can do a loss. The loss we chose, and the paper chose, was mean squared error, and then you sum all the losses from the independent multi-layer perceptor networks. You backpropagate, and do gradient descent in each of those independent MLPs, and then as you proceed through training, the loss should decrease if you're doing things right. So our results is on the full NoProp architecture across the full MNIST data set. We achieved a test accuracy of 0.94 with a train accuracy of 0.97, almost 0.98, which is worse than the paper's claim for the architecture. They got 0.995, which rivals and is even slightly better than just standard convolutional neural networks. So it was a little bit disappointing that we weren't able to replicate A, their results, and B, this gave us being me, far less confidence that we'd be able to show anything meaningful with respect to catastrophic forgetting, which is kind of the core question of what we were trying to answer here. One being, like, can we run and re-implement the paper's architecture? B, can we show that it actually does anything for catastrophic forgetting? But looking at this, I mean, you can see some goodness happening here in that it's not trivial. It's not as if we're just randomly classifying things. It's definitely learning something, and the fact that it's doing so in these independent MLP blocks is interesting and valuable, but it's unfortunately we weren't able to achieve the results in the paper. So here's a visual demonstration of what we were able to achieve and predict after training on the whole data set. You can see in this case, obviously this is just a random selection of digits. We had an error rate of 1 out of 15, which is anecdotally not bad. So then moving on to our catastrophic forgetting experimentation and discussion, the way we chose to do that was based off of, again, another person's implementation of how to test for catastrophic forgetting, where you train your neural network on MNIST, first on a subset of MNIST with only containing 0, 1s, and only containing 2, 3, then only containing 4, 5, etc., etc. And in doing that on, standard fully connected or convolutional neural nets, you obtain pretty terrible results after each switch of the data set. In that, like, you can do whatever subset of the data set, you can classify that very well, but then it tends to completely forget how to classify everything else it was trained on before. And there was no exception here that the exact same thing happened. Even though we were using this application of diffusion modeling, it unfortunately did not play a role in aiding us in reducing catastrophic forgetting, which again, it was just a little bit disappointing that we weren't able to see any positive results. But in some sense, the negative result is also useful. It doesn't necessarily mean it's not useful at preventing catastrophic forgetting altogether. On the MNIST dataset, using this particular architecture, though, it does pretty much mean that. But what you can kind of see, and I think you can honestly see it better if I go to this next page with the chart, is how for our first sequence where we're only training on 0 1s, we got great accuracy on 0 1s, not on any of the other digits, which makes sense, right? That's all we had in the data set. Then as we move on to training on 2 3s, training on the model after it had learned the weights for 0 1, it completely forgot how to classify 0 1s. These are the test test sets. So it does include more digits, but yeah, it was pretty terrible. The results for the next version of catastrophic forgetting, training the network sequentially on 0 through 7 and then 8 to 9, with our thesis being like, okay, well, maybe the subsets we chose just weren't generalizable enough for the model weights to be set to an optimal place. They were in an optimal position for that subset, but maybe if we do a wider version, that optimum would be better set for the whole range of classifications, the whole range of labels, which again didn't pan out in practice. So we had our 0.95% or 95% accuracy for 0 to 7, and then again it completely forgot how to classify 0 through 7, and then got really good at classifying 8 9 after that, which you know, and I should clarify, it wasn't the test accuracy here, it was the training accuracy numbers here, not test. So we encountered some difficulties in trying to reproduce the paper's claimed accuracy of 0.995 on MNIST, but we got 0.94% test accuracy with the full network and train at 0.9798, which, as we talked about, it's not trivial when you're only conducting that backpropagation locally on noised MLP blocks. So it is still an interesting result, just weren't able to quite replicate to the level that the paper was able to, which again I think signals real value in exploring this type of architecture. And then we weren't able to see the improvement in catastrophic forgetting, which the paper didn't claim, it just kind of hypothesized and said for future exploration that it would be an interesting thing to explore. Though as we thought about it more, again, we being me, it does make some intuitive sense that this wouldn't necessarily improve catastrophic forgetting. Like on first glance, when you think about it, there's a sort of truthiness to it, that in these independent MLP blocks that are independently sort of noised, that the fine-tuning, you might not get as much catastrophic forgetting, but you're changing the loss function as you're training those weights when you're adding those new data sets dramatically, such that it doesn't necessarily matter that they're independent blocks. The loss function is still dramatically different than it was in the first time. What you would have to do, I think, to actually improve catastrophic forgetting. Obviously, there's the ways of like trying to seed the former data in such that there are uh, parts of that data that the loss function can kind of pick up and re-optimize on the whole data set. But you would have to find some way to do that, or otherwise make the loss function slightly more generalizable, rather than just classifying on the data you have. So here are references, and an acknowledgement that some of the visualizations in the paper were from the presentation, as with some of the code, but we also did a significant amount of our own development and contributions to that. So happy to take any questions via email or Canvas. Thank you for a great semester. Have a good one. Bye.